Welcome to The Explainer. Today we're diving into a really cool concept that sits right at the intersection of biology and, believe it or not, high-stakes game theory. We're going to uncover the hidden logic that drives some of the most dramatic conflicts you see in the animal kingdom. So let's kick things off with a puzzle. You've definitely seen this in a nature documentary, right? Two big animals, maybe they're fighting over food, maybe a territory, and there's all this roaring and puffing out their chests and all this dramatic posturing. But then, a lot of the time, one just backs down. No epic, bloody battle. Kind of makes you wonder, why? Why waste all that energy on showing off instead of just going for the win? It feels a little weird, a little illogical, but this isn't about being weak or cowardly. It's actually about playing the long game. What we're seeing is pure strategy, an optimal solution that evolution has stumbled upon over millions of years. And the craziest part? The animals don't have to think about it at all. To really get our heads around this, we can use a simple but incredibly powerful model called the hawk-dove game. It was developed by this brilliant biologist, John Maynard Smith. He had this amazing insight that success in evolution isn't just about being the biggest or the strongest. It's about playing the smartest strategy you can against everybody else. So let's imagine a population with two basic behavioral programs an animal can run. First up, you've got the hawk strategy. A hawk is just pure aggression. It escalates every single time, and it will fight until it either wins or gets seriously hurt. And then you have the dove strategy. A dove would much rather just posture and display. The second its opponent actually attacks, the dove bails. It retreats immediately to avoid getting hurt. Okay, so in any of these conflicts, there are really only two things that matter. First, there's the value of the resource, which we're going to call V. That's the prize, the food, the mate, whatever they're fighting for. But second, and this is just as important, there's the cost of injury, which we'll call C. This is the huge penalty you pay for getting into a real fight and losing. All right, let's walk through the 4 ways this can play out. If you're a hawk and you meet a dove, great news. It's an easy win. The dove runs, you get the whole prize V. Now, if 2 doves meet, they'll do their little display, but eventually they just share the resource. Each gets half the value. If you're a dove and you meet a hawk, you flee. You get 0. But hey, at least you don't get hurt. But, and this is the big one, what happens when 2 hawks meet? Well, they fight. It's brutal. Each one has a 50-50 shot at winning V or losing and paying that massive cost of injury, C. So, which one's better, hawk or dove? To figure that out, we have to run a little thought experiment, one that kind of mimics how natural selection works. We'll ask, what happens if a rare mutant strategy pops up in a population where everybody else is playing the same game? Can that new guy, that mutant, invade and take over? First, let's picture a world that's just full of peaceful doves. Sounds nice, right? But then, through some random mutation, a single aggressive hawk is born. What do you think happens to it? That hawk cleans up. It's like a king. In a world full of doves, it never gets into a dangerous fight. It just bumps into dove after dove, and every single time, it gets the entire prize with 0 risk. Its success is off the charts, and that hawk gene is going to spread like wildfire. So what this tells us is that a population of pure doves, well, it's not stable. It's just waiting to be invaded. Okay, so a world of doves is a no-go. Let's flip it. What about a world populated entirely by aggressive hawks? Now that's got to be stable, right? A population of fighters should be tough to invade. Well, it depends. And this is the really key insight. The stability of a hawk-only world depends entirely on that relationship between the cost of injury, C, and the value of the resource, V. And for most animals, let's be real, a serious injury that could get you killed is way, way more costly than losing out on one meal. So for our purposes, let's assume C is much bigger than V. So, in this dangerous world where fights are super costly, let's imagine a single mutant dove appears. It's completely surrounded by aggressive hawks. You think it's toast, right? But here's the amazing twist. That lone dove actually does better. Think about it. All the hawks are busy fighting each other, and they're constantly getting seriously injured. But our little dove, it just retreats every time. Sure, it gets a payoff of 0 in every encounter, but here's the thing, it never pays that massive cost of injury. And in a world where everyone else is getting hurt, getting a 0 is actually better than getting a negative. The dove strategy can invade the hawk population. So what gives? A pure dove world gets invaded by hawks, and a pure hawk world gets invaded by doves. Clearly, neither of these pure strategies works on its own. Evolution has to settle on something else, something that is, by its very nature, uninvadable. And that brings us to the formal definition of an evolutionarily stable strategy, or just ESS for short. Basically, an ESS is a state of balance. It's a strategy that's so good, so perfectly adapted to the game everyone else is playing, that no newcomer with a different plan can show up and beat it. Now, for a strategy to be an ESS, it has to pass two tests, and it's a really clever bit of logic. First, it just has to be a solid strategy. No mutant can show up and get a better score against you than you get against yourself. Simple enough. But what if a mutant does equally well? That's where the second rule, the tiebreaker, comes in. In that case, your strategy has to do better against the mutant than the mutant does against its own kind. This basically ensures any little group of mutants can't get a foothold and will just fizzle out. So what's the ESS for our hawk-dove game, assuming fights are costly? Well, it's not a pure strategy at all. It's a mix. The only state that can't be invaded is a population that has a very specific, stable fraction of hawks and doves living together. The exact ratio depends on the values of V and C, but the real takeaway is that the stable outcome is this beautiful balance of aggression and caution. So far, we've kind of assumed that all the players are identical. But the real world is messy. It's not always a level playing field. What happens if we add a simple, observable rule that breaks that symmetry? Let's imagine one animal is the current owner of a resource, like it's sitting in its own nest, and the other is an intruder. This one simple, obvious difference completely changes the dynamics of the game. It creates what we call an asymmetry. And with this new information, a totally new ESS can pop up. It's called the bourgeois strategy, which is a fancy name for a simple role. If you're the owner, act like a hawk. If you're the intruder, act like a dove. Now, think about what happens when a whole population follows this rule. Conflict just vanishes. Intruders always back down, owners always keep their stuff, fights are avoided completely, which saves everybody from that potential cost of injury. Now, the rules of the game can also be changed by something a little less obvious than ownership, and that's genetic relatedness. This becomes super important when we start looking at how animals in the same family interact. See, when you're dealing with a sibling, you share a ton of your genes, and this fundamentally changes the math of survival. Helping your brother or sister succeed is, in a very real genetic sense, helping a part of yourself succeed. So a strategy's fitness isn't just about what you get anymore. It's about its effect on your relatives, too. Because of this, cooperation can actually become the winning strategy, an ESS, between family members, even in situations where being selfish would be the smart move with a stranger. And this brings us to the biggest, most mind-blowing takeaway, and it's captured perfectly in this quote from Maynard Smith himself. None of these incredibly complex, mathematically perfect strategies require conscious thought. The animals aren't sitting around with calculators trying to figure out the payoff matrix. Evolution itself, just by acting as a kind of randomizing device through endless trial and error over millions of years, can arrive at these incredibly sophisticated solutions all on its own. It's this powerful, hidden logic that's shaping the world all around us. And it really makes you stop and wonder, what deep, evolutionary games are we humans playing every single day without even knowing it?